Hello and welcome to another Siblings in Science.
I'm Joseph.
And I'm Bradley, and we've done that the wrong way round.
Oh. Oh well.
So what are we talking about today?
We're going to talk about nuclear reactors.
Okay.
Yeah.
Bit of a change in subject from
Washing machines.
and putting trainers in washing machines.
Yeah, so...
what is a nuclear reactor?
So a nuclear reactor is something that uses the energy produced by something called nuclear fission of uranium, so uranium-235. And so nuclear fission is when you have a nucleus, so the thing that atoms are made of. So at the center of every atom. So let's start with the bigger picture, I guess. Okay, so you have a table. Table is made out of what?
Atoms.
Atoms, exactly. Atoms are made out of three main constituents of an atom.
Protons, neutrons, electrons.
Neutrons and electrons, exactly. So the
GCSE physics. Chemistry.
Physics. It's a bit of both. It's important both. So do you know where the protons and the neutrons are in an atom?
No.
Okay, so they're at the center.
Right.
It's like a little solar system. The solar system analogy kind of breaks down when you get into quantum mechanics. But a very simplistic or simplified view is that it's like a solar system. You have the protons and the neutrons in the center, which represents what's at the center of our solar system.
Me.
No. Apparently not. Copernicus said it wasn't. So the sun, center of the solar system, and then the planets
go around
it. Yeah, exactly. So the nucleus is basically the sun, and then the planets, the electrons are basically planets. And what happens in nuclear fission? So this is not nuclear fusion. So I'm saying fission here, like F-I-S-S-I-O-N or something. And that's when you have a nucleus that is quite large. It's got nuclear uranium-235 has like 235, whatever. I think 235 protons and neutrons, I guess. And that is uranium-235 splits into two, or splits into multiple pieces. It actually splits into more than two, so it will split and then it will also release neutrons. And those neutrons, it will split into two roughly equal bits and then release a few neutrons along the way. And those neutrons are key to how nuclear reactors work. So when it splits, it releases energy and heat, and that goes into creating steam. So nearly all forms of power. So can you name any forms of power?
Like coal.
Yeah, so coal, wind turbines.
Yeah.
They all work by rotating something.
Yeah.
So they all have like steam or whatever. They heat something up, or they have something that turns. So like a windmill, it turns the blade, and that turning process is what creates electricity. So the nuclear reactor will create steam, and then that will rotate a turbine. So this release of fission, this fission process where a large nucleus splits into two roughly equal bits, but then also releases a few, like 3 or 4 neutrons. That is key to how nuclear reactors work, because those neutrons, they hit into other uranium atoms. So yeah, nuclear reactors use uranium, and they hit into other uranium atoms. And that causes them to split, and which releases more neutrons, which hits more uranium atoms, which cause them to split. And for a nuclear reactor to get what's called, I can't remember what it's called now, but to get like a critical mass, I guess, of stuff, you need, for each decay, for each fission, you want on average 1 other fission. Okay? So that releases energy in like a chain reaction sort of thing. And that chain reaction is what releases the heat. So we're going to move tone very quickly to what other things do you think uses nuclear fission? Where does nuclear come into it? It's on the news,
what nuclear power?
And then the other
nuclear warheads.
Yeah, so nuclear weapons. Okay, so nuclear weapons work slightly differently. So they have two separate bits of uranium, which are below the critical mass. So they're not going to release much energy because for each neutron, on average, they're not hitting another uranium atom. So you don't get this chain reaction sort of thing. It kind of dies down. So what happens in a nuclear bomb is you have a conventional explosion, which brings those two bits of uranium together. And that means it goes above that critical mass. And then, on average, you have, for each uranium decay, more than one other uranium decay. I say decay, I mean fission. And that releases an enormous amount of energy, and that's how nuclear bombs work.
And what's the difference between nuclear fission and nuclear fusion?
So fusion is when you have two very small atoms and you bring them together, and it creates a larger atom.
And what do you use nuclear fusion for?
So currently we're not using it. There are some experiments going on in Europe, which and probably the rest around the world as well, which are trying to make nuclear fusion energy gaining, so that you get more energy out than we need to put in. Currently, I think we're almost there, but we're still having to put quite a lot of energy in to get the energy out. Fusion is far more like accessible. It uses like hydrogen atoms, and there's hydrogen coming up your tank, so it's much easier to get the stuff. Like uranium, you have to enrich it for it to work.
So nuclear fusion in 10 years' time?
I don't know. I don't really know enough about it to comment on timescales. But I would say I think we will improve significantly in 10 years.
And with that prediction, we'll leave you. Please send in your complaints if 10 years' time that's not true. We've been Siblings in Science. See you next time.